Hi, I'm Donnell Roberts, author of Particle Mechanics. Today we're going to explain how magnets work. Now, how do you make a magnet? All right, you take copper wire that's coated and you wrap it around an iron core. The more wraps you have, windings, the more circles you have, the stronger it is. So you have circles at the core, you run an electrical current through it, and you'll have a north and a south. And it will form what's called magnetic lines of force. So what we're going to do today is we're going to add to the magnetic lines of force and show you that they're actually particles traveling in a circle. So first, I would highly recommend, these are, you can see them here, these are iron ferrite magnets. They're the weak kind. You know, they stick together. Well, the first thing we're going to do here is you have a north and a north. Now, when you push them together, once you get a certain distance, you can feel a circle all the way around on both sides. Both magnets are pushing away in a circle. That's the first question. Why do the magnetic lines of force have a circle around them? So we're going to show you with a little demonstration here. Now what I did was I took, this is just copper tubing, and I just took it like this, and I made a coil. All right, so then as you do this here, we have a north and a south, and you're assuming you're running electricity to it. Magnets without electricity do the same thing. So then the other thing that I did was on this outside circle, all right, let's call this is called the inner magnetic circle, or the spine of the magnet. Now, this circle that comes out and moves in a circle is the outer magnetic ring, or we're going to call it the magnetic rib. All right, so since it's north and south, this one travels in a circle, up, up, and out. So now on the other side here, we have another magnet, simulated magnet, that has the north, all right, and the south. This particle comes out and goes this way. And so there is a flow of particles. That's the key to this. The particles flow in a circle. So now, as we put these two magnets together, just like we did the two iron ferrite, move them together. So what happens as we move these together? As you move them together, what you'll see is these circles come in contact with each other. Now, based on the way of the flow, all right, particles that flow in one direction will go out and around on the flowing out is going to go on the inside. And since these particles are flowing the opposite direction, they're flowing like this, they cannot go to the inside of the rib. All right, it's going to push, just like any flow, just like water, you squirt somebody with a hose or the wind blows you, a flow pushes. All right, we're going to take another breakaway here. Water flows very similar to how magnetic ribs flow. Now, whenever the flow is in the opposite direction, that's what we want to show you here. So this would be two magnetic ribs here, and as they're coming together, what happens when they collide? See how they deflect each other? There's a deflection point right there where they start deflecting. So now, have my assistant put the rib under the other way, right there like that. So we have one above Notice how you have one above. So when the other one comes underneath, it cannot go into the flow. So what it does is it pushes right there on the outside of the magnetic spine. So whenever it pushes there, it's going to push away. And that's how this works, is based on the flow of these magnetic ribs around the magnetic spine. See how it pushes it up once it collides? Notice it's pushing it up. It's just like a flow of water. But it can't go in that way. Notice how they collide. So it has to go on the outside of the magnetic spine. So let me show you this. All right, give me the other two. Let me show you this. Hold that other one out there. So what you have is, you have your normal rib that's going just like it is, flowing this way, and then you have the other one flowing the opposite direction. So since it cannot go in there, it goes underneath, and that's what pushes magnets apart. That's the repel force based on the flow, the directional flow of the magnetic ribs. So then what you're going to do is, this one is going to push right here, and this one on this side is going to push on this one right here. So when the two of those push, that's why magnets push themselves apart. And the other thing is, you can literally feel, let me turn this a little different here. You literally can feel the circle around as you're going. You can feel it on both sides. So does this model, using a magnetic spine and magnetic ribs, explain why magnets have a push apart in a magnet? Now, whenever magnets are closer together, you only have to move them a little bit, and it gets twice as hard to push against the other one, but you can still feel that circle. All right, why is that? Well, what we're going to do here is we're going to shove this closer together, all right, just like what I did with the two magnets. I've already done that. So now this rib, all right, is intersecting, all right, with this rib on the other side. So it's pushing the second rib. I don't know if you can see it or not, but that's what we got. So now what we do is we're going to add this to the inside ring here. And then as you put this one is going to circle around north to south, can't fit in because of the flow, and it's going to push on this side, twice the pressure. So then when we add this one over here, same thing. Notice how you now have rings pushing, two of them on one side, pushing two on the other. That answers the question as, why do you get closer? Does it just get way more powerful? Of course, now I've got 3 coils here. So if you go to the 3 coils, it's going to be 3 times as hard until you get to the very center, where it's going to be as much as it can do. But that's what it is. It's literally pushing itself apart due to the flow and the direction of the particles against the ribs, against the spine. The rib pressure against the spine. And that's what you do. It's just because it won't go in the same side, different direction, it pushes it both ways, which is exactly what you get when you feel it. That's why it pushes in 2 directions. All right, now, the next thing we're going to do here is we're going to show what happens when you flip the magnet over. So you see here I've got north, north, south, south, like where we left off. That's the way these 2 magnets are. All right, so now pull them apart, north, north, and you flip one over. So when you flip it over, what's different? Well, the push turned into what appears to be a pull. So when you get your two magnets real close to each other, you can literally feel that same pull circle. It's a lot harder to do because it wants to pull you together. All right, so you can feel this same circle, all right, on a north, south, south, north. So what we're going to do here is we're going to take this here, this magnet on this side, we're going to remove, for simplicity, the magnetic rib from one side and put it on the other side, like so. We have this. Now, what's different? This particle is moving this way. Literally on the other side, it's moving the other way. So just like we turn the magnet over, we're going to turn this over. All right? Like so. Now, as we do this, all right, notice the flow. This one's going down, this one's coming out. So now, when you push the two magnets together and these magnetic ribs come in contact with the magnetic spine, which we're going to do here. We're going to show this one over here first. All right, now as we come together, what's it going to do? These are going to flow the same way this flows. You can see it right here. So as you pull it here, which side of the rib is going to go in? It's going to go on the inside. And notice it hooks in. It's going to the inside of the magnetic rib. This one is going to flow the same way, like so. All right, we're going to take a break away from what we were doing to show you that water flows almost identical to the magnetic flow of the ribs. So one of the things is when it is the same direction, when the flow is the same, watch. Notice how that flows together. They flow together and they do that. So now, what we have here is this is an intermagnetic ring. Hold it right there. I got an assistant here. Hold it right down there. So what happens is, on one of the rings, it already has a flow going this way. So when the other ring, the other magnetic ring from the other ribs, once it comes up, it will flow on the same side. Notice how that additional pressure pushed what would be part of the magnetic spine. Notice how it pushes it down. So what happens is you have doubled the flow. So what it's doing is it's going to push this magnet as it comes up, and this intermagnetic ring flows the same way. It's going to push it that way. Now let me show you with the rings the same thing. So what happens is you have a magnetic rib on a magnetic spine. So when the other one comes up, once you get here and it goes in, just like that, that flow pushes it that way. And that's how that works on every single magnetic rib and magnetic spine. It pushes it that way when the particles are traveling in the same direction, based on the north and south configuration. So now, when you do the magnets the same way, they stick together, they pull together. See how they stick together? What do these do? They stick together. Real simple. It's literally, you take the magnetic lines of force, turn them into magnetic circles, all right? And wherever the flow goes, it is. So now what's happening is both of these are literally, this flow is pushing this magnet and the flow is pushing this magnet. Now, it's pretty simple to see. As we get closer together, it will hook in, we'll do this here, it will hook in to the next ring, to the next ring. Now, you will also have, and this is real hard to show, but now you'll have another magnetic ring pulling. And so whenever these magnets get closer, I highly recommend, if you're going to watch this video and you don't have these iron ferrite magnets, get the little cheap ones. Get them, because then you can just feel how much difference the power is. So if you look at it here and you just imagine once it gets closer, you're going to have 3 pulling. And that's what it does. It literally, it looks like a pull, but it's the flow, where the flow is pushing with the flow of the magnets. Now, what we're going to do is we're going to turn the magnet back over like we were. We have north, north, all right, north, south, north, south. Now we're going to add another magnetic line of force here. All right, so as you go through here, one of the things is you're literally going to have these circles or these ribs around the whole thing. I got a little model here. If you can look at it, this is how it's going to look, except you're going to have multiple rings, how many windings of your coil, and these ribs are going to form. So for simplicity, we're only going to show one on each end. So we added one there. Now we're going to add one on the other side. Like so. So now, put them together, north, 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 and as you pull them, put the 2 magnets together. As you do them, as you go over, you feel the circle, which we showed you before. You feel the circle, and then once you get over the circle, you get a pull, and it pulls down. All right, so as you're going across, it snaps in place. Why does it do this? Well, with this particular geometrical model, it's pretty easy to see. Now, as the 2 models come across each other, like we saw before, this circle pushes away because of the flow. Different flows, it's going to go on the outside, and you're going to feel the circle until you get over here. And then what's going to happen? What is producing the pull down? As soon as you get to the side where it can hook in, notice this flow, all right, is going to go to the inside, and it's going to pull your magnet down just like we did there. Back up a little bit. Just like the magnets pull each other together, all right, and then they line up. So then as you get them on over, you go just a little bit further, all right. This is going to hook into this rib here, and as you get all the way over, this one is going to go through this rib here. I think. If I can get it, I don't think I can get it quite right. All right, so as you see it here, I've got my own little geometrical problems here, but I'll get it here in a second. It's going to hook in there, and this one's going to hook in there. There we've got it. All right, it's a little hard to show with this model because of the flow, but notice all the flows are the same. It pulls to the inside, all right? You know, like magnets, you could put a piece of cardboard between the magnets and they'll stick together on the cardboard. Those particles just flow through everything, all right? Copper, when my model here doesn't, just to give me a little bit of a brick. But now, see how this hooks together and it holds, all right? And it holds, all right? So, and it's because of where the flow is on the thing. Now, when you take these magnets, you just drop them by each other. They always line up perfectly. I mean, have you ever seen two magnets you drop together? You get them rare earth magnets, you can't even hardly get them apart until you pull about halfway, then they'll come apart. All because of the way these particles are moving and where the magnetic circles or the ribs are pushing on the spine. So that's why it always lines up, and when the closer they get, the more of these are going to line up, all right, and pull. That's why it gets closer, it gets stronger. So now, if we take our two magnets, north-north, flip it over, what do you get? You get a pull, all right, you flip it over. You get a pull, they pull themselves together. If you feel the pull, and it goes over here, and then once you get to the middle, you start to get a push. And then when you go all the way over, you get this perfect push, and these are hard to push together, all right? So what we're gonna do, we're gonna flip north-south over, and then we're going to move it this way. So as we move these through here, right there, this one's going this way, all right, it's going to the inside. So as you're pulling this over there, over the top, you're going to get the pull, just like we showed. And then as you go on over and you get closer, once this gets to the other side, it is now pushing. It is now pushing away. All right, so then as you come all the way across, what are you going to get when you get across here? You're going to see this perfect push that you feel away, because it's pushing on the outside or the top of the ridges or the magnetic ribs. So does this model explain the geometry of the atom? The answer is yes. Not only yes, it's a perfect yes. Now, what I did here is these are a bunch of little magnets. You put them all together in a cylinder, all right? And they get a little more powerful than what you had before. But when you put the north-north together, the pull pulls evenly, all right, on the side till you get up around the top, all right? So now, when you turn them over, all right, you get north-north, and you can feel the push and it slides along here. So now one of the things that they do is to figure out the pattern, and this is where a lot of confusion comes from. Whenever they try and do a pattern of this, all right, you use ferrofluid, which we have some, we're going to show that, and they also show magnetic filings, all right, and they'll see a pattern. Well, one of the things, if you put these atoms together, north-north, because south-north you can't put together, if you put them together like so, what happens is you will start to see what happens when you put magnetic filings. Now, one of the things is there's a smooth edge on the outside of this because they're all this, but what happens right here? All right, so you see these, and it happens on the other side too. You have this one going down, this going down, and just imagine hundreds of these or thousands of these magnetic ribs and where they cross. So whenever you drop your magnetic fillings or filings in there and you test a magnet, just remember you're going to have these cross points where magnets are going to stick and point certain directions. So when you look at magnetic filings, try and fill in where the magnetic circles or the magnetic lines of circles, not magnetic ribs are. And that helps you with that. All right, now what's the overall shape, all right, of this model? What's the overall geometry? Well, what we see here is if you add magnetic ribs, what you're going to do is you're going to have magnetic ribs all the way around this, all right, in all directions. Because you turn a magnet, twist it, it don't matter what direction, it works the same. So does this geometrical model explain that? And the answer is yes, it does. So one of the things I'm going to do here is I made another model just so you can see it. All right, if you look at it, it's donut shaped. All right, so you have your coil, your magnetic ribs, and you have, well, it's just one set of, or you have your magnetic spine and you have your magnetic ribs going out. Now, one of the things is, if you take this, all right, and you put this under ferrofluid. Now, ferrofluid is a fluid that's got a bunch of real fine iron in it. That's why I call it ferrofluid. And you stick a magnet to it, it does real cool stuff, all right? So in my book here, it's Particle Mechanics. I have 62 pages on magnets, some of my best work. But on page 107, what we have here is a picture of the ferrofluid. And what does it show? Now, it's not perfect. What you have to realize is the iron follows the strongest point of the magnetic ribs, all right, as it can, and then it drops off, all right? So it's not going to form something better than what it can with gravity. But what do you see? You see this. You see this. It's there. So now, as you can see here, north-south, north-south, all right. Notice this smooth edge on the outside. So what we're going to do is we're going to show a stack of magnets that are north-south under ferrofluid. Now, in my book, all right, on page 311, you get a picture of the ferrofluid. All right, what does it show? It shows these ribs coming out, all right, and you can see them, and it shows this smooth edge. All right, so does this model explain what we see in ferrofluid? And the answer is yes. But also remember, when you do it under iron filings, take into account where these ribs cross, all right? And it's going to give you a different pattern. It's not going to do what ferrofluid. Ferrofluid went on where the strongest magnetic points or the magnetic circles or the ribs were. So does this model, the geometry of this model, work? Yes, it does. If you followed any more my theory, you notice I have something called the key ring atom, and of all things, it has a torus structure the same as the torus structure. Torus structure means donut shaped. They're starting to see this more and more all the time. So my theory, I did it 25 years ago when I first came out with it, but magnets and the atoms work very similar with the same movement and with the same interaction. Remember, physics and chemistry are easy with the correct geometry.